Hey guys, Keith here. So the video I'm about to show you was recorded at the recent 2021 Sydney Mini. It's a largely whiteboard orientated presentation where I talk through exactly how your data is handled from the time that your effect is rendered through to when it turns up on your lights. And through it I explain a number of concepts that I don't think have really been explored on any other videos out there. This is my first attempt at it. It's largely unscripted. Obviously I'd done some thinking about what I wanted to cover, but I didn't really have a highly structured presentation to it. So if it rambles around a little bit, just put it down to the fact that it's the first time I've given the presentation, and most other presentations I've done many times before, and I'm pretty comfortable with the sorts of things that I need to cover. And who knows, maybe in a year or so's time I'll do another follow-up which might be a little bit more structured. But for now, this is probably the only video out there that I've seen that goes through and explains exactly how your pixel data is handled and interpreted, everywhere from the controller tab through to your show player, whether it's xSchedule or FPP, and how that gets out to your controller, what your controller does with it, and how it ends up on your lights. So enjoy, guys. Thanks.
What I want to try and do is explain how your data is handled, how xLights handles your data, where it goes, how it gets into the FSCQ file, what it looks like in the FSCQ file, what it looks like, how does it get onto the network, what does that look like, when it gets into your controller, what does your controller do with that data before it eventually gets out onto the wire going out to your pixels. As ever, I'm happy to take questions at any time. So if I start to lose you, if I explain it poorly, I've thought about how I want to explain it, but I haven't written a presentation, not really my style most of the time. So let's add an Ethernet controller here. Let's add a couple of Ethernet controllers here. We're not actually going to output anything, but that's okay. 192.168.0.45, it really doesn't matter. Let's add 10 universes of a very convenient 100 channels. Convenient because when I draw it, the numbers are nice and round. Let's add another Ethernet here. We're not going to do serial. The concepts are very similar. It really doesn't matter. 192.168.0. It really doesn't matter. 78's fine. Again, let's do 5 universes of 100. Just so that it's not just the same. All right. So if you look here, it says that it's allocated 1,500 channels. So what does that mean? Well, effectively, xLights has allocated a block of memory where this is the first channel here, and this is the last channel down here, okay? And it's just a block of memory, right? Which means it's a whole bunch of just slots where a number between 0 and 255 can be stored, okay? And there's 1,500 of these slots in memory, okay? Now, furthermore, what we've said is that if this is number 1 and this is number 100, then that is going to be the end of the universe, and this one, which is 101, all the way up to, I don't know, let's imagine 200 ends here, right? That's another universe of data, okay? And then we'll start with 201, and we'll go all the way up to 300, and that will be the third universe of data, okay? Big chunk, just broken up into batches of channels, right? And the thing that's significant about these is that this is eventually going to be sent out over the network, right? And when it gets sent out over the network, it gets put into an E131 packet or an ArtNet packet. And DDP is similar. The only difference with DDP is it would be much larger, and we'll talk a little bit about DDP later. An E131 packet, and an ArtNet packet for that matter, has a header area and it has a data area. The data area is quite simply a block of these channels, 1 to 100 or 101 to 200, okay, in this area here. The header area is a bunch of information about the data that's being sent. The vast majority of it is waste, and this is the problem with E131. You know, it's one of those situations where people think that, oh, it'd be really good to send all of this information, etc. The reality is there's about 3 bytes worth of information that's useful. The rest is crap, right? Now, that's crap in most circumstances. Sometimes there's uses for it. This header is 126 bytes, okay? So for our 100 bytes of data, we're sending 126 bytes of header information, right? You can see how that's a little bit wasteful. Obviously, these are typically 512 bytes. The wastage is not quite as much, but it's still pretty high. And this is why protocols like DDP are popular, because the wastage in the protocol is so much less, okay? For comparison, the ArtNet header is 17 bytes. The DDP header is 10 bytes. Okay? There are some features that E131 supports that these protocols don't support, however. But to be honest, I'm willing to bet none of you are using them, so it doesn't really matter. The useful data in the header is basically, you know, maybe the count of bytes, the universe number, and I think that's it. There is a sequence number in there, but generally speaking, other than telling you that packets seem to have gone missing, the sequence number's not really depended upon for anything.
Does it carry things like destination address, things like that?
So it does. That's kind of buried up in the Ethernet frame itself. So it's an Ethernet packet, right? And an Ethernet packet is 1,500 bytes, right? And so you can see that it doesn't even use the full Ethernet frame as well. So that's also wasteful, right? With DDP, however, it will use the entire frame, okay? So what will happen with DDP is slightly different. When you define a DDP output of, I don't know, let's say 10,000, right? What xLights will do behind the scenes is break that 10,000 up into blocks which are 17 less than 1433 it is once you take out some of the frame header stuff. And that's how much data it will pack in each packet. And then when the controller receives it, it'll reassemble it all. Okay? But that's how that overall absolute channels, we used to call them absolute channels or xLights channels, gets broken up into your universes, packaged up into your network packets and sent across the network. Now, if you run something like Wireshark and you put output to lights on, you can capture and look at these network packets and you can see the universe number and everything inside it. It's pretty straightforward to do. Yes. That's one network packet. So you've got 126 bytes in the header and 10 bytes of data.
So it's always one universe per outgoing packet.
Always.
Doesn't matter the size. What's in it?
Doesn't matter the size, etc.
Only for E131.
No, that's true with ArtNet as well. DDP, because you tend to define large blocks, xLights then breaks them up into network packets that match these 1,500 bytes so that it fits in, because you can't send it all in one piece. You've got to remember, we are sending the data to some pretty low-end hardware at the end of the day. Controllers do not have CPU cycles to burn. They tend to support the most basic elements of the protocols, right? So you don't generally get to take advantage of advanced network capabilities. You know, there's not a controller out there, I don't think, that supports IPv6, for instance. You know, generally speaking, they don't have SSL support or any of that sort of stuff. That's all overhead the controller just cannot afford. Okay? Does that make sense? Everyone's good with that? All right, so let's talk about models then. So the next thing that you do is you go into here and you create a star. Okay? And you put the star like that, and maybe we create another star. These are 50 channel stars. And you can see by default it's allocated a channel number to it, right? Now you might have expressed that in terms of universe start channel. You might just, in this case, it's just used the absolutes. And what that's saying is, where in this map does the star exist? And so as much as I'd like to use green, I won't. And so the first star starts at start channel 1 here, goes all the way across here, gets up to channel 150, and that's the end of the star. It's using all of those channels. So when the data goes across the network, it's part of the first universe, and half of the second universe will contain the data that's eventually going to find its way to the star if we've configured everything correctly. The second star is going to start on channel 151, and it's going to conveniently end on channel 300. So it's going to be half of the second universe and all of the third universe. Okay? And sent over the network. But how does it know where everything is? And the answer there is that xLights, when it generates or creates this star, it does two things. It generates two values. One is it generates a position that it's going to use to display it on the screen. Okay? So it works out whereabouts you need to put something to make it look star-like. What it also does is it generates an XY coordinate for where in the buffer it's going to be. Now this can vary because when you get into the sequencer and you start to choose different buffer styles, those locations are going to be different. And when you create a submodel, that stuff's going to be different. Right? So behind the scenes, xLights can move a lot of stuff around. But at the end of the day, pixel 1 here is going to be associated with those first 3 channels. And when the data gets put onto pixel 1, it's going to write the data into these first 3 buckets for each frame. Now, if you've got multiple layers and you're blending stuff together, before the data gets written to these locations, it's going to do all those calculations. So it calculates each layer independently. It starts at the bottom and works out what does that effect tell me about that pixel. Then it goes to the next layer and it says, what does that effect tell me that that pixel should be? It then looks at the blend style and says, how does the blend style tell me that those two things should come together? Should this top layer overwrite the bottom layer? Should it average them together? Should it take the maximum value? All of these things are possible through those blend styles, etc. And it works its way up the stack until it gets to the top and it's got a final value, and then it writes it into this square. And it does that once per frame. So I've drawn a buffer here with 1,500 channels. In reality, xLights, immediately after that buffer, has another 1,500 channels starting at channel 1. This is frame 2. This is from 0 to 50 milliseconds. We're doing 20 frames a second. This is the 50 to 100 milliseconds frame. And it's got a whole new buffer to write the data into. Okay? All right, so the first frame, it'll do all the layers, finalize the value, write it into the slot. It then goes to the second frame and does the same thing again. And the same thing again all the way through to the end of the sequence. This is why, as you can imagine, xLights uses a fair amount of memory. For a long song, lots of channels, you're going to end up with a lot of memory consumed. It's even worse if you turn on the render cache, because the render cache actually has a separate set of memory where every frame, every layer is stored as a set of values which it can then pull from quickly when it's doing the rendering. So that's why if you turn render cache on, your memory consumption of xLights can absolutely explode. It can use 16 gig, 20 gig of memory if you've got the memory there for it to use. But it makes a big difference to render time, so particularly if you've got a big show, it can be quite a popular thing to do. Now, the only time that it doesn't work this way is when you turn canvas mode on. Canvas turns everything on its head. because that simple start at the bottom, render those pixels, next layer, render those pixels, merge them together, move to the next layer, and so on until you get to the top. Canvas mode totally screws that up. Everything gets done out of order. Things get done multiple times. And that's why canvas mode can be quite slow. But the trade-off was some of the things that you could do with canvas mode, so it's there. And that's also why you will get warnings in check sequence if you try to use canvas mode on an effect where canvas mode's not required. It warns you about it because it slows everything down. It causes over-rendering to occur, and you don't want to do that. The place where it gets even more interesting is where you create groups. Groups can create a situation where multiple pixels end up in the same buffer location. Okay? And this can happen where you've got generally you've got a fairly big display and maybe you've got one prop and you shrink it down really small on the display. Because as I've discussed previously in my buffers and layers presentations, the way in which the group buffers are created, I'm talking about the default buffer or the per preview buffer, if you like, in a group, is it looks at all the dots that are on your whole house display, wherever they happen to be, and you might have a lot of them here in your matrix, etc. What it tries to do is it tries to overlay a grid. And xLights tries really hard to create this grid such that every one of those dots appears on its own in one of the boxes. Okay? But when you create a group, you get this maximum grid size. And what the maximum grid size tells xLights is, as you try and create this grid and get it such that every single pixel is on its own inside a box, you are not allowed to create, in this case, more than 400 columns or more than 400 rows. Right? And so depending on what your layout looks like, if you've got a really big display and a really dense matrix that looks quite small on the display, it's not going to be able to slice everything up such that every pixel on that matrix is in its own block. And so what ends up happening is you get multiple pixels inside a single cell of the render buffer. And all that happens then is when it's writing the data into here, right, it will write the same value for the same cell for all those pixels into all the areas of the render buffer here that happen to fit in that same cell. So it'll work out that cell needs to be green, and so it will go to every pixel that's in that cell and write the data into that particular pixel's 3 channels and say, that pixel's green. Okay? So if you want to take a group and make the effect quite grainy, just reduce that 400, take it down to 20 and see what it looks like, right? It basically creates a 20 by 20 grid and lots of pixels will be in each square on that grid, right? So it'll be quite blocky. If you make that number really large, obviously it creates really large buffers and that's slow to render. So you probably don't want to do that a great deal. And that helps you, so that's how the data in your sequence finds its way into this data in memory. Now, this buffer sits in memory, and xLights does not save it to disk while you're using it, okay? At any time. Autosave doesn't save it to disk. Autosave will save a copy of the XSQ file to disk, but it will not save a copy of the FSCQ file. That just sits in memory. To get that written to disk, you've got to save your sequence, okay? It doesn't save it automatically. And when you open that sequence up again, it will read all the render data out of the FSCQ file that matches the XSQ file that you opened into memory, and that becomes the in-memory copy of the sequence. That's why if you delete the FSCQ file and you open up your sequence and press play, it's black. Why is it black? Because there was no data, right? But if there was an FSCQ file there, and it was, let's say it was an FSCQ file, an old FSCQ file, it might be totally out of sync, right? And that's when a render all kicks in. You click render all, and it rewrites all of this data into memory. That's exactly right. That's why you should always do a render all before you send everything off to your show player, because you want everything perfect. Now, xLights does its best to keep this buffer up to date. Every time you touch an effect, xLights re-renders that effect. Not only does it re-render that effect, it re-renders every other effect that might have had an impact on that effect. And so you can get what's called, it's a render explosion, right? Particularly if you've got a long effect on a group, right? It can trigger everything to render just because as it starts to render this thing, it says, oh, well, that overlaps with that thing over there. So now I have to go and render that, and all of a sudden, everything's getting rendered, right? And xLights slows down. This is why if you sequence just on models, right, you'll get the best performance out of xLights. What will happen is all your threads will be used, right? I've seen 16 core CPUs running at 100% rendering xLights because people rendered at the model level, and so just everything could happen in parallel. Once you create groups, xLights has got to look at things and say, well, I'd love to render that group, but it needs to wait for that model. And so when you look at xLights render, first of all, you've all seen the progress, right, when xLights renders? Yeah, you've clicked on the progress bar at the bottom and had it come up and show you everything. So first of all, you see only a certain number of them are green. The reason for that is because xLights only has a number of render threads that is proportional to the number of cores on your CPU. It's not 1-to-1, I think it's 1-to-7, I think it is. And that's just a balance of not everything can render all the time. It might be waiting for disk, etc. So we use more threads, okay? You'll also notice that certain lines get stalled and seem to be running and moving in step. You'll get one that moves ahead and then everything else moves up to it and stops. And then the next one moves up and the next one goes along, right? That's because there's a dependency between the two. And so those render threads cannot progress any faster, typically, than a group that contains that model. But it's higher up on the stack of models to render. So that's why that happens. And it's just trying to make sure that when it finally gets to a point of calculating these values, that the values are final. All the things that could happen are final. All right. So then, you've got your FSCQ file. We haven't talked about our FSCQ file. So what does an FSCQ file look like? Well, an FSCQ file looks like this, with a header on top. And that's it. It is literally just a copy of memory. That's why saving the FSCQ file, even though it's really large, takes almost no time at all, because there's no work to do. All we've got to do is stick a header on top, and we write the whole thing to disk, okay? And although it's a lot of data, it's just a straight memory dump. It's really quick. The header itself doesn't contain a huge amount. It has things like the frame time. Is it a 50 millisecond or a 20 millisecond? It'll tell you the number of frames that are in the thing. It'll tell you how big each frame is. If it's got audio associated with it, it'll tell you the name of the audio file that goes with the sequence. V2 files, there's 4 formats of FSCQ files. The V1 format is by far the simplest. It's why the F16 V3 uses the V1 format. It's absolutely trivial. It is literally this, the header and all of the data just dumped into a file. The V2 uncompressed, very similar. There's a few differences in the header. It does have the sparse ability, so it can say, rather than writing all the data into the file, it can say, well, our second controller, which I can't remember what it was. Where's my mouse? So our second controller here goes from channel 1001 to 1500. So what it can do is it can say, actually, this is a sparse file. I'm only going to write the data that belongs on that controller. This is what you do when you have a master remote. You send a sparse file up. And so what it will do is it will actually leave this data out. it'll write the header, then this data, and then that data from the next frame and so forth. So it basically drops all the data that that controller doesn't need. In order to do that, the header contains a table that describes the sparse layout. Okay? Right, it just says what channels are included. Now, it allows quite a complicated layout. It doesn't have to be contiguous or anything. The F16v4 can handle sparse layouts, but it expects the channels to be contiguous. You can't have crap all over the place. It just, way too much processing. Keep it simple. So that's that. Then you get to the V2 xlib and the V2 Z standard. The Z standard is commonly supported by FPP. The F16v4 will use the xlib. Dan implemented the xlib when he implemented the Z standard because he realized that on lower end controllers, that the Z standard, it requires 400K of memory just to decompress a file. Whereas the xlib, you can get away with 40K of memory. It's like an order of magnitude different in memory consumption. And the way that works is essentially what it does is it takes this data, it breaks it up into chunks and compresses it into little zip file blocks, essentially. Okay? And so the data doesn't on disk look like this, it just looks like these blocks of gobbledygook, but they're just zip files effectively. And so the controller reads the compression table to see which blocks are there, which channels are in, or which frames and channels are in each block, right? And then you can decompress them on the fly and recreate these buffers. Okay, but that's the difference when you use those compressed formats. And the compressed formats can also be as sparse as well. So you can be compressed and sparse at the same time. Again, it makes those files a lot smaller. So that's the FSCQ file format, which then gets uploaded onto your show player, regardless what sort of show player it is. Now let's talk about what our show player is going to do. Yeah, I'll talk about that. That's in our show player. We'll talk about that. There's two different mechanisms depending on whether it's an audio or a animation. They actually work slightly differently. So we've got our FSCQ file, and let's pretend it's not compressed, it's simpler. And we've got our frames, and we've got our show player, and our show player is trying to play this song. So what's it doing? Well, let's imagine it's an animation. We'll stick with an animation first. It's the simplest. So what it does is it starts off playing it. It says, I'm at the 0th frame. So it goes and it reads the 0th frame into its output buffer. Right, reads it all in. It then says, how am I meant to send this data out? Let's imagine our show player is sending the data out over the network. So it needs a description of the universe structure. And so it looks at this and says, okay, well, that's universe 1, and that's universe 2, and that's universe 3. So it takes that data, it slaps a header onto each one of them, and it sends it out. Okay? And typically it sends it out pretty quickly, but it takes time, right? So in my performance testing on the V4, xLights is sending 196 universes in about 5 milliseconds. Okay? But it's not 0. Right? Everything takes time. And this is why when you're playing audio, when you're doing your lights, always go early. Right? If you know how the frame doesn't always perfectly line up with the audio and am I going to go a little bit late or a little bit early? Always go early. Right? Because there is always going to be a lag between the reading of the data, the packaging it up, sending to the controller doing its bit and putting it out onto the pixels. You're going to lose something like anything up to half a frame in time, just waiting for all that stuff to happen. So go early. Always go early. So yeah, so it reads all of that stuff in, it packages it all up, and it sends it out to the network. and it's an animation, so it moves on to frame 1, 50 milliseconds later or 25 milliseconds later, it reads in frame 2, typically into the same block of memory, the same mapping to the universes, and it writes it all out again. Okay, if it's DDP, obviously it's probably written it into a big block, and then on output, it says, well, that's bigger than the 1400 odd bytes that I can output to DDP, so it fragments it up into multiple DDP packets, and it writes those out. Similar sort of concept, okay? But show players can do more than that, right? Show players can do things like what Darryl was doing earlier on FPP, where he was running event playlists, etc. So hypothetically, your show player can be reading from multiple FCQ files, potentially covering different ranges of channels. I assume FPP, I don't know, but I assume that you can control how that data gets merged together where two channel ranges clash. I don't think it always overwrites. I think it used to, but I'm not sure it still does. And so all the show player is doing is, instead of just reading the data in, putting it into the memory and sending it out, it might read the data in, read this data in, merge the data together, and then write it out. Or it might apply an output processor to it, where it might have something that, having read the data in, goes and applies a brightness overlay, or remaps some channels around, or lots of other things, right? There's lots of things that the show player hypothetically can do to the data before it goes and puts it into packets and sends it out onto the network. Okay? We good there? Questions about the show player? Have I missed anything? I don't think I have. Audio. Audio is different. Here, it's just counting up, right? It starts at 0, and every 25 or 50 milliseconds or whatever it happens to be, it knows that it's onto the next frame, and it reads the next frame, and off it writes it. Audio is different. So the sequencer will have an audio player, right? And the audio player is a ravenous beast, right? You start feeding it data, and it's always wanting more, and there's nothing worse than not serving the beast at the right time, because you get weird dropouts and clicks, and makes your show sound awful very, very quickly. So when you kick your sequence off, it goes and starts loading data into the show player. Now, on a high-end thing like xSchedule, etc., where there's heaps of memory, it sends it all at once. It says, here, I have it all, right? And the audio player just goes off and starts playing it. On the F16 V4, I don't have anything like the memory for that, right? So I'm receiving interrupts every now and then saying, I'm running out of data, give me more, give me more, give me more. And I've got to keep running back to that SD card, bring the data in, fit it into the audio buffer before it runs out, otherwise it's going to drop out. We don't want that. But what the show player is doing here is it has no count and no idea where it's up to in the sequence. But what it does do is every 25 milliseconds or 50 milliseconds, depending on your frame timing, it goes to the audio player and it says, audio player, where are you up to? And it says, I'm at 3 seconds. It says 3 seconds. 3 seconds, 20 frames a second, that's 60. I need a frame 60. Let me go and get frame 60. Let's bring it in, package it up in a network packet, send it out. Okay? And then it will go back 50 milliseconds later, ask again. Okay? Now, the beauty of this is that if this thing lags for some reason, okay, then maybe it doesn't come back around in 50 milliseconds. Maybe it comes around in 150 milliseconds. Right? So when it goes and asks the audio player, where are you up to, it says, I'm at 3.150 seconds. Right? And so it says, I'll jump over 60. I'm at 63. Give me 63. Let me get 63 out the door. And that's why, even if there's lag, your show player's playing up, etc., it will still somewhat match the audio. It might still look laggy because the performance may impact on things here as well. Who knows? but it's jumping through frames, etc., trying to find the frame that matches the audio every time it outputs. The beauty of Ethernet is that it's a very, very low overhead to send it out. You know, up to a point, right? If you're running an original Pi, it topped out at about 120 universes before it just couldn't keep up anymore. These days, with a Pi 4, it's substantially greater than that. And that was largely down to the internal way that the network adapter was connected to the processor on the Pi. It went through a USB 2 port internally. You didn't see it, but internally it did. And that limited the bandwidth of the data that could be sent out. When that happens, what can happen is things can queue up. If things queue up too much, things start to break. In the case of a case like the Pixies, Michael's talking about the Pixies, where you're sending the data out over a serial connection, that's often a synchronous process. It's not run in parallel. And so if I'm trying to send the data out, instead of sending the data out in 2 or 3 milliseconds, it's taking 60 milliseconds. That's where the lag will start to appear in here. Now, it won't lose track of the song, but it will drop frames. And that's still lag, right? You know, if you've got something that's meant to be a smooth fade and it's doing every 6th frame, it's going to look really chunky instead of smooth, and you're going to hate it. And you go, or you're doing singing face, and you know the faces are all lagging, etc. So that's where the lag's going to come out. And that's what happens on the Pixies. That just backs up to the point where xLights will write the data into the thing, and the serial port will come back and say, I just cannot take any more. I am full. And so it blocks and waits. And when it blocks and waits, it delays the frames. Okay? The xLights output to the Pixie, what it actually will do is it will actually stop sending data to the Pixie. In order to stop it impacting everything else, it'll get to that point where the serial port's starting to say, I've got too much data, and then xLights will just say, well, I'll give you a break, I won't send it to you. You're not going to deal with it at any rate, so I'll drop this data so I can keep doing the other stuff that I need to do. Yeah. Either way, it looks crap, right? At that point, you're throwing your Pixies out like you should have done on day one. There's a latency there. Look, you won't notice it 99.9% of the time, but there's a latency. Things are largely done sequentially. There is flags in xLights and on FPP as well, I think, where you can turn it on and say, output all the network packets in parallel. In reality, of course, it's still a single pair. It's not really parallel. What it's doing is it's basically saying, oh, I can be in parallel. Let me throw all this at something that's going to do it serially at any rate. There are different reasons there's different things that are slow, and so doing that can still give you improvements because it might allow your I/O to work better or your processing to be more parallel or whatever else, so you can still get a benefit from it. But at the end of the day, it's going to whack all that data out over a wire to a switch, which is going to go to another switch or to the controller, etc., and that takes time. xLights will typically send, and your controller as well, so FPP or your show player, will send it out in the order. So, you know, if you've got all of that data there, you know, you've got multiple controllers, each with a large block of channels, it'll start at 1, send all them out, then go to 2, send all of that. It doesn't interleave them. It's this block, that block, and so forth, and send it out. And so on a large show, yeah, not everything's going to arrive at the same time. Now, there are technologies out there. DDP supports it, ZCPP supports it, and E131 supports it. Not necessarily in every controller or implemented well in every controller. But what it does is you can set your controllers up in some of them to say, use synchronization. And what that tells the controller is when you receive all of this data, take all the data in, process the data, get everything ready, but don't send anything. Wait until I tell you, because I'm going to send you one packet at the end. I'm going to send it to all of you. And when you receive that packet, then you can all send out at once. And hypothetically, that gives you a very synchronized show. In reality, you probably just get every second frame that's highly synchronized. Just because in order to do that, basically, it's impossible to, if you're sending a large amount of data, if you're sending a small amount of data to each controller, they're probably going to deal with it fine. But if you are trying to smash 1,024 pixels out on the controller, it takes a frame to send that time to send that out. There is no time for all of this, receive the data, wait for the special word, then send it all out and be perfectly synchronized, right? It can't happen. In fact, controllers don't necessarily send your data all out from just a single frame at a time. You can get what's known as frame tearing, where half the data's from one frame and half the data's from another frame. You commonly see this on panels where you've got a really dense thing and you'll see tearing in the frame where you seem to get half of one frame and half of another. And that's just because every controller makes trade-offs about how they do things, and in some circumstances, particularly under high load, you just get this tearing. You don't run too many pixels on a controller, you won't see it, but you run lots of stuff, you'll see it from time to time. And if they're avoiding it, they're probably avoiding it by being very structured in how they do things, which means they're probably dropping frames, etc., because it's probably the only way they can achieve it for large volumes of data. Small volumes of data is fine. All right, let's talk about then what happens when it gets to your controller, because it's not as simple as getting your controller and going out on the wire. Controller's got to do stuff with it. So let's talk about what happens there. All right. So my data's arriving in network packets. So the first problem with my data arriving in network packets is they arrive fast, right? I'm getting 192 of these things in 5 milliseconds, right? I do not have a lot of time to think about what I'm going to do with that data and where it's going to go and all of that sort of stuff. Now, some controllers get away from this by basically not giving you the ability to do much to the data. What you send to the controller is what goes out on the wire, and your older controllers were very much of this structure. You couldn't do a great deal. Things like the Falcon and the FPP controllers give you things like virtual strings, and you get a lot of things that you can do to the data. Even the SAN devices lets you apply brightness and things like that. That stuff requires you to do something to the data before you send it out. So, I mean, I've looked at several of the controllers. I haven't seen the firmware of all controllers, but typically you will need a block of memory, right, which often called a descriptor table or something, which is basically where does the controller's network throw this data as it comes in. It doesn't necessarily need to be big enough to handle every packet that's coming in, because it's going to be processing them. It's not like it's not processing anything at all. But it needs to be reasonably deep because so much data is arriving so quickly, and you can't let it back up too much, because if you can't handle it, then it's back at the switch. And now it's UDP packets, so there's no retry. If you don't take it when it arrives, the network's not going to resend it to you and say, oh, don't worry about it, I'll send it to you later. No. It just disappears, right? So you've got to have a fairly deep descriptor table to take the data in if you're accepting a lot of data, okay? There's a fair chunk of memory that goes there. The next thing that you need to do is you need to take that data and lay it out according to the input structure that you've defined. The Falcons, FPP, etc., allow you to lay, which universes go where. It doesn't have to be just a block of universes incrementing, right? You can put them in the wrong order and everything else. So you're going to need somewhere that you can put the data, and you can say, well, actually, no, that's universe 1, so that goes there, and that's universe 10, so that goes there. So you're going to have to start moving the data around and putting it in so that all the data is now in the order that the controller kind of definition says that it's going to arrive in. Now what you need to do is, and these aren't necessarily separate buffers, they may be, they may not be, but now you need to go and do things like apply, you need to move the data to the output type structures. And with things like virtual strings and the like, they're not necessarily just a direct copy, right? You might have to move things around. You might have defined zigzagging on the controller, so the channels go this way and then they go this way, and so you have to reorder everything. You might need to apply brightness or gamma, or insert some null pixels, right? All of those settings on the pixel outputs page on the controller, all of those things now need to be applied. And the data basically needs to be put into its output format. All right, so, and this is where all of your strings and your virtual strings and your brightness and your gamma, etc., get applied. All your data's sorted out like that. Now you've got to start thinking about, I've got to push this data out over the wire, but you've got a problem, okay? All of this data is, at this point, probably in order, so the first byte that needs to go out is there, and then the second byte that needs to go out there. But controllers don't necessarily send the data out that way. Often what they'll do is kind of turn the data around 90 degrees. And what I mean by that is if I've got a buffer here that's got channels 1, 2, 3, 4, etc. for output 1, and for output 2 I've got channels 1, 2, 3, 4, etc. and output whatever I've got. Often in the hardware, what it does is it actually wants to output the first bit of each one of these first. So it has to go across all of these bytes, grab the first bit, and that's what it actually writes out. And then it goes to the second bit of all the channel 1s, and it writes that out. And then it goes to the third bit and writes that out, right? Because it's typically got an output command that writes multiple ports at once, and typically it's a bank of 8 or a bank of 16 or something like that. I call this sort of transposition because you're kind of transposing everything sort of on its side. Now, sometimes you don't need to do this. The FPGA in the Falcon 3 didn't really need to do this. It was quite capable of doing that on the fly because it's like multiple CPUs in the FPGA and it could do this. The V4 has to do this sort of processing. The FPP, well, at least on the BeagleBone, it's not such a problem because the Pi Hat doesn't really need to do this. The Pi Hat uses basically SPI and it's only got a couple of outputs. So it just writes the data out directly. Whereas the BeagleBone has got a companion chip associated with the CPU and a lot of this processing, as I understand it, occurs there. And this writes all the data out onto the output wire, okay? Typically in batches of 8 or 16, but sometimes one at a time, and pushes it out to your pixels. And your pixels basically act like shift buffers where the data is shifted in, and once it's full, it then passes it off to a PWM. The PWM basically turns the power on and off at a frequency according to the brightness. So when you send a 255, it pretty much just turns it on. When you send a 0, it turns it off. You send a 128, it turns it on for half the time and off for half the time. Not for half a frame. They run at a higher frequency than the frame rate, so it will turn it, but it will still be turning it on and off for about 50% of the time to create 50% of the brightness and 50% of the current draw. And that's how the data finally lands on your pixels and gets displayed. Now remember all of the things that have happened here from your show player, right? It had to read all of that stuff in from disk, potentially apply some transformations to it, put it into a network packet, send it over a network through a switch, possibly multiple hops, land it here in the descriptor table, move it into the input format, then reorder it all into your virtual strings, then go and apply all of these transformations, finally to send the data out, and you've got 1,024 pixels, so that's taking a full frame of time to send out. Things don't actually arrive at your pixels until probably at least one frame after they were meant to, remembering that we triggered it all over where we actually were in the song. There's a lot of stuff that happens here to get your show player to work. So, no. Yeah, that's right. Now remember, that's right. You pay. That's right. You don't. You've obviously got the video card to display it, etc. But the lags are quite low. And so, yeah, your show will always be. Now remember, we're talking a 20th of a second or a 40th of a second. Most people aren't going to notice it, right? You know, if your audio is out by a 20th of a second, you're generally not going to be put off by it, right? It has, I can't remember what the number is. It's like 100 or 150 milliseconds that it has to be out before you really have that. The audio's just not right. Yeah, your brain's actually pretty good at dealing with that sort of stuff. The problem is you know, because you've got multiple controllers, the latency is actually slightly different on each one. And this is why, like I say, I go back to that simple rule of when you're unsure about whether to go early or late, go early, right? Not a lot early, but go early. Yeah, because there is always going to be lag in the playing process, right? It's not so much that you have to be thinking about it while you're sequencing, but it's there, and if you're on a half frame, always go early. Well, yes. Well, really modern stereos are atrocious. In fact, there's nothing you could do about that, right? That's typically half a second to 2 seconds, right? Depending on the car and potentially the settings that the person's used. Typically, yeah. Typically, they're trying to deal with, you know, any uncertainty around receiving the data or whatever. And, you know, when you're listening to free-to-air radio, it doesn't really matter if it's a half second or too late. Right? You've got no idea. That's right. That's right. And that's why it's always amusing. Every year, right, 2 or 3, 4 times a year, there'll be some post around, oh, why can't we do audio to someone's mobile phone? Right? And you see it all the time. And the challenge there is all of this sort of stuff. You've got to push the audio over it. You've got to synchronize it. You know, quite frankly, it's hard enough to get people to visit your show's Facebook page, right? Getting people to go to all the trouble to go on and just so they can hear some audio that's probably not going to be in sync at any rate, I just don't think it's real.
The best option, full stop.
Yeah. The only place it might work is if you've got a big drive-through where everyone is really invested in seeing the display, etc. Sure, maybe, right? But then you've still got all the problems of latency. And you know, those latencies are going to be generally way more than the latency you see here amongst the pixels. So do I. I run a speaker. I don't run it at high volume, and people complain about how low the volume is. I say, well, step closer. Oh, I find it needs to be loud until about 9 o'clock, and then the insect and bird noise dies down, and it goes a long way. Yeah, I mean, we live on a cul-de-sac. It's reasonably quiet, but once the sun goes down, all the insect and bird noises stop. The audio goes a long way without you turning it up very loud. Yeah, I doubt anyone can hear my audio inside their house. Outside, yeah, maybe, but it's not loud. So multi-sync over the network? Yeah, I can talk about multi-sync. What do you want to know? So the difference with multi-sync is, okay, so how multi-sync is handled depends a lot on your network infrastructure. Hypothetically, the way multi-sync work is I send out a packet to a multi-sync address. There's a number of reserved multi-sync addresses. For E131, every universe has got a unique address that you send data to if you want to multi-sync it. Okay? Now, hypothetically, that goes to your show switch, your switch, and what the switch does is it says, oh, okay, that's interesting. Has anyone asked me for that data? Okay? So it's got a table that says who is interested in seeing what. Okay? And if no one's registered interest, the switch just drops the data and the world moves on. Okay? So if you've got a controller that is registering for multicast data, and if you set a Falcon up, every universe you define, it will go to your switch and it will say, hey, if you see any data for this particular IP address, which is that E131 universe's multicast address, I want to see it. Okay? And so when that multicast data lands on your switch, it will have what's known as an IGPMP lookup table, right, which will say, oh, this IP address over here wants to see that data, and it will pass it on. But multiple controllers can register for the same universe. and they will all receive a copy of the data. Now, the reason, and this was particularly true when people were running low volumes of channels, is it's obviously a super easy thing to configure. You just configure the universes, they're all multicast, you configure your controllers, the controllers say which channels they're interested in, and they pull the data down. It's just not that efficient. It's on a wired network with a reasonably competent switch. It's quite efficient, right? Great for media broadcasting and things like that. The problem is A, not all consumer-grade switches really implement those protocols. They just broadcast it. Everyone have it, okay? The other problem is it can cause you problems in Wi-Fi networks. Now, the problems with Wi-Fi networks are significant. As long as you can keep your multicast data off your Wi-Fi networks when they don't need to be there, you're okay. But if you're running network infrastructure that's blasting out multicast data into your Wi-Fi domain and no one in the Wi-Fi domain really is interested in it, it's just creating clutter that's going to upset things. So, but to be honest, I've read a fair bit. There was a number of posts on do-it-yourself Christmas around this, and you know there's people that speak quite passionately on both fronts, right? There's a number of people that say if you're doing Wi-Fi, you should do multicast because and I don't remember all the arguments, but I think it had to do with some acknowledgement and everything that wasn't so necessary. And I've heard others suggest that you should do everything unicast. I don't know. I've always just made it optional and let people decide what they want to do and what they get the best experience from. I got to say, I have not quite managed to unpick it all. I do know Wi-Fi networks. Your biggest problem with Wi-Fi networks is you only have to have one device that's receiving quite poorly that it can start to impact, particularly if you're broadcasting data, it can slow your whole network down. And that's why I would never recommend Wi-Fi. It's okay if you're doing master remotes, that's fine, it's low volume, it's generally not that time sensitive, but sending pixel data over Wi-Fi, it's always going to be a problem. Right, if you're like my house, I have 7 adults watching Netflix, right? You don't want to be putting your show data on that, not because it's going to upset their Netflix, because of the other way around. I don't care about their Netflix. But yeah, you want as consistent performance as you want, right? Remove the variables, and setting up a separate show network, it's not highly complex, it's not highly expensive, right? You can pick a router up for $40 or whatever retail. You know, if you want to get them from China, they're even cheaper. You can pick up 4 ports for $7 or $8. It's cheap as. I would always set up a separate show network whenever you can. There's no reason not to. If you're running a 10-100 switch and a large show and lots of people watching Netflix, then it's going to be working hard. If you're running a reasonable quality gigabit switch, it probably handles it in its stride unless you're running 1 million channels or something. You know, we worked out, I think you can run 1.5 million channels on a gigabit switch. You'll use about 60 or 70% of its capacity. That's using E131. DDP, you'd get considerably more before you start to run into issues. You're close to that? No, well, no one needs to be. Most people that are running large amounts of channels are running P panels, and they should be running those in master remote at any rate. So their networks are generally no busier than mine, and I only run 15,000 pixels. It's not a big show, but I don't run any P panels. Mine's worse. I run 3 8-port 10-100 switches, daisy-chained. So it goes through a local one, then it goes outside into one, and then it goes on to another one. It's fine. Oh, actually, no, I forget. There's another one also downstairs on the end of that chain as well. It's fine. Oh, but it's all one flat network. It's all one flat address space. Yeah, no, but if you're having problems, separate the network. If you're not having problems, let it be.